Hey, hello, can you hear me?
Hey, what's up, man? I can hear you.
Okay, great. Yeah, let me see if the stream has started. It seems like it has. Okay, great, great.
Can you post it?
Okay, yeah, so we'll get started here in a sec. Okay, well, hi, I'm Jerry. I'm the head tutor for Signals and Systems here. And so this is the review for Park's second exam. I guess it's the first one this semester because of how COVID and the winter storm and everything worked out. So what we're going to be covering today is basically everything from the beginning, all the way from what a signal is, up to convolution, up to what you've been doing since the first exam was supposed to be. So basically Fourier analysis. So yeah, how I usually structure this review is the first part is I go over the theory, and then the second part is essentially just me spending time trying to solve examples, problems that you might want to get out of this review. I'm very open to requests in that respect. So today is going to be a little bit different. So the first part, the first hour and a half I have scheduled is just midterm one exam, or just midterm one material. So we're going to be covering up to convolution, basically. And then I'm going to be covering examples as I go through there. And then up to the halfway point of this review is going to be Fourier analysis and midterm 2 stuff, essentially, in what would be a normal section of this course. So, yeah, if there's no questions right now, I'll go ahead and get started on material. I'm in also, if y'all want to ask questions live during the review, whenever y'all get in here, there should be a message at the top that says I'm in tutoring room 1. So yeah, I'm there. I should be speaking through the mic, and yeah, if y'all want to chime in during this, that would be great. I would appreciate any kind of things that would help direct how I give my information here. So yeah, yeah. So let's go ahead and get started. So well, I'm going to start at the very basics. What is a signal? So a signal, in the context of engineering, is essentially just a set of data. It's going to depend on some other variables. So a lot of times we'll write them as functions. So say f of t for continuous time, and we'll have functions in discrete time also, but they're going to be indexed by say an integer, say n. So if we were to plot just some function, yeah, some continuous time signal, it could be like a sinusoid. Yeah, something smooth, essentially. Something that could be smooth. It exists in a continuum. Whereas if we have a discrete time signal, it might look like a series of spikes. We could draw it like that. Yeah, so this is just a series of delta functions. But we could also have something that looks more like what we would see in a computer, a list of numbers. So this could also represent a discrete time signal. Yeah. So both of these are valid representations of different types of signals. Yeah, these two aren't equivalent, but yeah. Also, in this representation, we might draw an arrow to indicate, well, that's the 0 point. So in this talk, I tend to like to talk about what's called the support of a signal. I'm not sure if this is a term defined in your course, but yeah, essentially what I mean by that is if we have like some rectangle, the support of a signal talks about the domain. So this time, so this is the section of time where the signal is non-zero. So this would be this subset of the real line. So if you want it written out, so that the support of some function is going to be the set of t values, such that so our x of t, our signal, oh wait, no, we called it f, right? f of t is not equal to 0. So this is just going to, this might come up if when I just start rambling. This is just the language I like to use. So let's see, we tend to like to classify signals. So one way that we will typically distinguish between them is aperiodic and periodic signals. So what is a periodic signal? So if we have some signal, x of t, then it's periodic if we have the following equality. So x of t is equal to x of t plus big T, where big T is the period. So essentially what this would mean graphically is if we had a signal that, let's consider like a sinusoid. All this equality here means periodic. So all of this means is that we're going to find copies of some section of the signal, and these are just going to be copies that are repeated over an infinite number of times as time progresses. So basically that's, and this is contrasted with an aperiodic signal. So an aperiodic signal is like one of the following. So like this box is not periodic because we can't look at sections of this box and find copies. We can't find sections of the signal and find copies of anything. This is going to be an aperiodic signal. And also I'm going to talk a bit about when we start going into convolution and how to actually perform it. I might say the words piecewise behavior a lot. So basically what I mean by that is, so let's consider the following signal. So let's have it have one behavior over here, some other behavior here, and some other behavior like over here. So basically what I mean by piecewise behavior is within some region of the real axis, so our time axis, some portion of time, it's going to be acting like one function. So f of t is going to be acting like one function, so f1 of t, within some region, say like so t is less than t1 and t0. Let's call those t0 and t1. So for t is within t0 and t1, it's going to be acting like this function. And within the other two time intervals that I've defined, so let's call this point t2, this one t3, it's going to be acting like the other two functions in the other region. So it's going to act like f2 for t is within t1 and t2, and f3, it's going to be acting like f3 in t within t2 and t3. So basically, that's what I mean by piecewise behavior. I'm not going to get too caught up on singular points, so I'm not going to be talking too much about discontinuities, particularly in these piecewise defined functions. But if I get a chance, I might. So yeah, so we have signals, and I've tried to define the best I can what a signal is. So right, one of the features that we have with signals is that we can manipulate them. And so what this means is that we can move them left and right with a time shift. So if this is our signal f of t, then a shift to the left would be written as t of, so let's assume that a is greater than, say, 1. It's just some number. Yeah, so then a left shift would be a t plus a. And whereas a right shift will be f of t minus a. We can also move these signals up and down. So what we would do to accomplish that is, so if we wanted to go up here, say like this is y0. Yeah, so if we want it to go up, then we can go just add a number to it. So f of t plus a. And if we wanted to make our signal go down, so provide a negative DC offset, that's what we would call it in engineering sometimes, we can just subtract that same number. We can subtract any positive number, and we'll make our signal go up and down, basically. So we can also stretch and scale them. So if we have our same f, then a scaling where we stretch it out, so we make it longer, basically. Yeah, so this will be written as f of t divided by a. And if we wanted to shrink it horizontally, then we would write this as, yeah, so shrinking horizontally, these are all supposed to be the same value, basically, by the way. It's not shrinking vertically. So this is f of t times a. Right. And we can also stretch and scale them vertically. So this would just be accomplished by regular multiplication. So make it bigger. We multiply by some number greater than 1. So multiply the whole function. And if we want to make it smaller, then we go do. Yeah, and this is divided by a, f of t. Right. And another feature that we get is we can cut them off at some point. This is accomplished through what we call the unit step function. So let me define that real quick. So this is the unit step function, u of t, is equal to, so the functioning definition that we're going to use right now is, so for everything that's on the left side of the y-axis, then we're going to have 0, and everything that's greater than the y-axis, everything that's to the right of the y-axis is 1. So this is going to be drawn out like that. I'm not going to get into details about the behavior at 0 specifically, because most of the time this is a technicality that we don't care about as engineers, and a lot of people have different definitions for what goes on there. The one I particularly like is the one where it's defined to be half at the midpoint, but a lot of people are kind of gloss over this, and that's what I'm going to do in this review. So yeah, what I mean by cutting off a signal at some point in time is if we have, like, say, a signal and it's some decaying, let's say it's this exponential right here. So let's call this x of t. Then to cut it off at time 0, I'm going to multiply this by a unit step function. So this is going to be, so the red here is going to be our units. Let me put in blue. Let me use different colors there. So x of t times u of t. So if this is our unit step function, notice that it's, right. So if we multiply everything on the right times 1, then we just get our original signal back. But if we multiply everything on the left times 0, notice that it's going to get cut off. So in the end, this is going to give us a signal that looks something like this. It's going to look like a decaying exponential, but it's going to have everything to the left of it cut off. So that's what I mean by that. So another special signal that we have, it's going to come up a lot, is called the delta function. So I'm going to give a similar working definition. I'm not going to go through its definition as a distribution or anything like you might have seen in the course, but essentially the one that we're going to work with is it's going to be 1 at t equals 0, so, and then it's going to be 0 everywhere else. So you would draw this out as a spike at 0. And we also have the definition that we use is the one where it's a limiting case of like a box, and then we just continually just shrink it down. And this ensures that if we have the integral of the delta function, it'll integrate to 1 because we want it to have unit area. But this is not too important. So what I want to talk about here is that we can sample a specific value of any function. So let's take our exponential again. So if I want to take the value of at here, let's call this a, then I would multiply it times a delta function, which is centered at this a value. So I'm going to draw the delta function in red. So this is delta t minus a. Remember, because we can shift it to the right, and this would be minus a. So this would give us just a spike at that same a value, but scaled to the same value of our x of t. So this would be x of a times delta t minus a. Yeah, this is just a scaled delta. One common confusion is that we could have is that it just gives us a the value of the function, but no, this is not true. This gives us a delta function, a scaled delta. So yeah, that's how we can get a single value. We can get a value at any specific time by sampling it. So right, so we have signals. So that's great. It's a function. What can we do with that? So, and there's a lot of things that you can do with signals, but often the thing as engineers that we're trying to do is how do we get from one signal that's kind of useless into another signal that is way more useful for us. So in the literature we call it a system, something that manipulates a signal. So we will sometimes draw it as this box. Yeah, so if we have some system H that maps a signal to another signal, we'll typically denote the input a lot of times as X and then the output as Y, or at least that's the convention here in the course. And that's great. So we have a system right now, and it maps a signal to another signal. We get signals from other ones, and that's cool, great. But we don't know too much about this system right now, because right now this is just some other function. It gives us a signal. So this is typically what we call a black box. And one way I like to think of this concept is, say we have like a bunch of monkeys. We told, we gave one of them a typewriter and said, all right, so write Shakespeare. And then we come back later and it's just a bunch of garbage. Yeah, so the output here did not really depend too much on the input. It's just like, it's essentially random. And we can't really ask too many more questions about how the system operates. Like, if we added another monkey to the typewriter, would it be better, worse? Who knows? So one way that we get around this is that we design systems to have certain properties. So one of the nicest ones that we have is called linearity. So if we have some signal x and we pass it through some system h, I'm going to denote this as a function because, I mean, we're mapping a signal to another signal, so x of t. So this is how I'm going to write it notation-wise. So if we have another signal, if we have two signals, so x1 and x2, and they could even be scaled, so a and b. So, and then we pass it through h. So if we pass this scaled summation, we should get a scaled, this should give us a scaled version of the output of these two individual functions. So x1 and sum with b, h of x2. So yes, this is the definition of linearity. The next one that is also really important for us is called time invariance. So let's assume that we have some real number. Yeah, so some real number. Then if we have the same function passing through our system, so x of t passing through h gives us y, then a time invariant system will also obey the following. So if this is our assumption here, then x, so if we shift our input by just some number, let's call it t, and then we pass it through a system, we'll get the same output as we got before, only it's going to be shifted over by the same amount. And this is huge, because essentially this lets us kind of make sense of how time is going to work. I mean, we don't typically think that things are going to operate differently on different days of the week. But yeah, if we have our system obey time invariance, then it's going to satisfy this for us. So LTI systems are special because we can, so if we have both linear, we have both a linear system and a time invariant system, it's what we call LTI. And these are special because we can completely determine the output of our function, of our system, our map from a signal to another signal, via what's called the impulse response. So the impulse response is just the output that we get when we send in a single delta function. So if we send in delta t into h, then the impulse response will typically denote it as just the lowercase h of t for this system h. Yeah, this is the impulse response. Then we can write our output as what's called the, we can get the output using our input signal, and then we're going to perform a operation on our two signals called convolution. So this is convolution. And this is kind of a complicated operation, and we're going to get into the definition here in a sec. But it's doable, and it's really doable on computers. And yeah, it's great that we can completely predict the output here, given the input. And that's not necessarily something that we can do otherwise. So a few other properties that can be important for designing systems is one's called causality. So basically we're going to have our system H. So if we have x maps to y, then this y of t, this can only depend on past values of x. So it can only be some function of, so x of, I'm going to say x of tau, for such that tau is less than t. I guess that's how I'm notating it here. So that's, so just as a simple example, if we have a signal x of t, and then we put it into our system. Oh wait, no, wait, scratch that. let's say we have y of t is equal to, let's consider this an example. Yeah, so y of t, and this is going to be just, say, 2 times x of t minus 1. Yeah, then, yeah, this is of course going to be causal, because this only depends on t minus 1 at time t. Now, if we look at a very similar system, oh yeah, so the conclusion here is that this is causal. But if we look at a very similar system, y of t is equal to same multiplier x of t plus 1. So we're shifting our input forward in time. This would be non-causal, because this t minus 1, or this t plus 1, is greater than t. And that's always true. So this is non-causal. Right. So a closely related property is if the system has memory. So this is going to, so basically what I mean is that if we have y of t, so our output will be a function of, so if it has memory, then it'll just be some function of the current input. So the time, so a function of x of t. So a simple example is one where y of t is equal to, say, like sine of x of t, or, so that's y1, or y2. So another one that's also has memory, or has no memory. So this is memoryless. Is going to be, so x of t squared plus x of t 4 4 times x of t. Yeah, these are both memoryless systems because these are only functions of x of t. And a simple example where it is with memory, then the one that we could say has memory is where it depends on a shifted version of the input. So x of t, but if we incorporate information from x of t minus 1, or x of t minus, or x of t plus 1, or x of t minus 2, then this is going to be a system that has memory. Because it depends on values of x that are not currently present. So this one. So essentially that would mean is that the system would have to, if we were operating in real time, this system would have to store these two values in order to calculate this one, especially if we're not, if we don't already have the current, if we want something other than the current one. So yeah, those are two examples that illustrate memory. And then if we have a system that's stable, so we want our, so for any input that's reasonable, so then we'd want an output that's reasonable. That's basically what stability is about. So how this is defined is if we, our definition is called BIBO. Yeah, so bounded input, bounded output. This is our version of stability. It basically, if you have an input that is bounded, that is our version of what it means to be a nice signal in our case. So let's say it's for all t, then x of t is less than b. Yeah, it's just some number. It's has a maximum value. Then if we have this, then we should get some other bound on our output, y of t. So this should be less than some, say, by. And this needs to, yeah, so it's less than or equal to some by. And this is a finite number, so this is going to be less than infinity. This can't be plus or minus infinity. If it is, then this is not bistable. So yeah, that's and I'm just going to go through another example here right quick. I'll probably put timestamps for all these problems after I'm done with this review here. So if we have so x of t. So if we have y of t is equal to x of t minus 1. Yeah, a. A times t minus 1, where a is just some number. Then I'm going to check if this is bibo. So if we assume that x of t is less than b, yeah, so less than or equal to b, then if this is true for all t, then we also know that x of t minus 1 is less than b, because it's the same signal, it's just shifted over. Yeah, so this would imply that we would have our output y of t. Yeah, if we take the absolute value of that, yeah, so this is the absolute value of, so just to be precise, t minus 1, x of t minus 1, yeah, so this is the definition. We can take absolute values across both sides, and then if we apply this bound, then let me take this a value out, and we get x of t minus 1. I'm getting a bit ahead of myself. So yeah, if we take in this condition that we just arrived, then we can find that our output is also bounded. So a by the absolute value of a times b. And this is a finite number. Yeah, this is just some number. So this is a bistable system. Yeah, and that's stability for you. Right, so one thing that we want through what's called the energy. So, and this is, so say we have a signal x. Yeah, so the energy of x is defined to be the absolute value over the support of the squared absolute value of x over the entire domain. So if this value converges, if this integral converges and is finite, then this is we'll say that our signal x is what's called, why did my tablet stop writing? Yeah, so this is, okay, there we go. So we say that x of t is an energy signal. And right, so that's great, but this integral won't always converge. So to be more specific, we have, if we have a signal that goes to 0 basically at infinity, so yeah, if it goes to 0 at plus minus infinity, it's usually an energy signal. Essentially any aperiodic signal that we're going to be looking at are energy signals. And one other parallel concept is the idea of power. So this is how we will measure signals that don't satisfy this going to 0 at infinity. So this would be, the most common class of them are periodic signals. So I mean just any signal that's not going to be identically 0 at as we take the limit. So how this is defined, the power then is going to be, so if we have our signal x again, so the power p of x is going to be, say, an average value of our power. And we're going to try and take the limiting case of when, so that we can capture everything in our signal. So this is our definition for power. and it's the same inside x of t, absolute value squared dt. And that is our definition for power. And this is just for any general signal. So one important note is that if we're working with our periodic signals here, let me draw that in red. So if these things are periodic, then we can derive the following, that p of x, where x is periodic, so let me write that out explicitly, if x of t is equal to x of t plus big T again. So then this is just going to be the average of the values at over one period of our x minus t over 2 x of t. Okay, yeah, and this is going to be the one that you're going to be using if you're going to be asked to calculate power of a periodic signal. So say of a sinusoid or a complex exponential or some square wave, like these are all just examples of periodic signals. If we have a triangle, yeah. Anyway, so that's power, and that one's for periodic signals. Energy's for aperiodic signals. An energy signal cannot be a periodic signal. An energy signal cannot be a power signal, and a power signal cannot be an energy signal. Oh yeah, if this integral converges, it's a power signal. Yeah. So one thing I like to talk about, especially when we start doing problems, is algebra. So one thing that's kind of useful for solving problems is that convolution is very similar to multiplication of numbers. So essentially what I mean by that is if we have it satisfies a lot of very similar properties as multiplication. So I mean, if we have some number x, let me just write that out. So some number x, and then we multiply it times 1, then we get x. If we try to multiply x, y, and z, doesn't really matter which order we do it. Y, z, yeah, so we can switch parentheses around, and we can flip the numbers. Y, z, oh wait, x. Yeah, so here for convolution, this would be the analogous thing for having this x times 1 equals x is the delta function. So if we have some signal x of t, so I'm going to say x is a signal, so some real signal defined over its support, then x of t convolved with a delta function. This will give us the same signal, x of t. This is called the identity property. It's very similar to having a 1 in multiplication. Another property that it holds, that holds similarly, is the associative. So if we have x, y, and z are signals, then we can switch around the parentheses, and this will be used. Oh, shoot. And okay, so essentially convolution is kind of transparent in this way. It doesn't matter which order that we do convolution. Yeah, so this one is equal to x of t convolved with y of t convolved with z of t, where we convolve x and y first. So these are the same. And another thing is that it satisfies commutative property. So if we have x, y, and z still signals, then x of t convolved with y of t is equal to y of t convolved with x of t. And this is going to be useful for us because we can consider, and we essentially get a choice of which signal we get to consider as the system and which one we're considering the input whenever we start putting things into our LTI systems to get our outputs. So, and one last thing that I'm going to talk about here is that convolution satisfies the distributive property. So if we have some, if we're trying to convolve x of t with a sum of signals, so y of t plus c of t, then we can essentially just multiply across convolved with y of t, and then we can add the convolution of x of t and z of t. And this might not make this might seem kind of useless right now until we start solving problems, and I'm going to show you how this is useful. Right, so a few more identities before we start going over convolution. I'm just going to start solving problems there. So we need to know a few identities. These will make our lives a lot easier, especially in the examples that I'm going to give. So one consequence of that convolution, the identity property of convolution is x of t. So any signal convolved with a delta function, as we know, is the signal itself. So essentially this means is that the delta function makes copies. And and this is true even if the delta function is shifted. So if we get x of t and we convolve it with some delta of t, let's say it's t minus 2, then we'll get x of t minus 2. This shifts it over. This is just and this is huge. This lets us easily represent time shift. So I have a bit of a demo to show y'all. Alright, so just in case you're not convinced that it makes copies, okay, identity, alright, great. Okay, so yeah, if we have our triangle function, yeah, it makes a copy. The black here on the bottom is the convolution of these two signals defined up top. So it's just some triangle. Now, what if we had our delta function? Wait, hold on. Let me switch these two real quick, so that I can really talk about how it makes copies. So we have our signal. It makes copies at 0. So if we have delta functions which are shifted over, we get copies at those too, though. So this is just a sum of delta functions right now, and in red. And notice that we get a copy of our function at each of these spikes. So yeah, this is essentially what we get, no matter if we had one of these or many of them, because of linearity, and we can go to that. But yeah, we get copies. Let me go back over to OneNote. And yeah, so copies. Another useful identity is that if we have the rectangle function, so let me define the rectangle function real quick. So this is sometimes written rect. It's also sometimes written as this pi thing. Yeah, this upside down rectangle, I guess. And so this is just going to be 1 whenever t is less than, say, the period, t over 2, and t over 2. Let me write that a bit better. Yeah, so sometimes they write the period here, and it's going to be 0 outside of that. So this is just going to look like a box, which is 1 from t over 2 to t minus 2. If you see it written without this subscript big T, then you can probably assume that it's the standard rectangle. And that's just going to have a unit area. That's the big idea there. So from 1/2 t to 1/2 t. And yeah, these t's are just going to be replaced with 1. Yeah, so one useful identity, so going back to what I was talking about, is if we convolve two of these rectangles, then we're going to get the triangle function. So we're going to get a triangle. Let me make more space here. Yeah. So if we convolve two of these rectangles, convolved, and let's just say that they're the standard unit ones, so, and this is the same. So if we convolve these two, then we get a triangle function. And it's going to have, its maximum value is going to be 1, and then it's going to be defined for t minus, from -1 to 1. And this is the standard rectangle, or this is the standard triangle function. Yeah, so this would be written as a function, so t minus 1 for t is greater than 0 and less than 1. And it's going to be negative t oh wait, hold on, let me rewrite this. 1 minus t, and then this is going to be 1 plus t, where t is -1 to 0. Yeah, so that's our triangle function. Sometimes it's written triangle of t. Sometimes it's written with the cool triangle symbol. But anyway, this is what we're describing here. Convolve two boxes, get a triangle. That's the idea. And some other identities that are useful for us, especially when we're talking about energy. Yeah, so if we're talking about E of x or P of x, it might be useful to know the geometric series. This is particularly useful for for discrete time signals. So if we have x of n, so the geometric series is going to be the sum of some r value, which is going to be defined from 0 to 1. It's not going to be exactly 1, and it's not going to be exactly 0. So yeah, if we sum just a bunch of exponentiated versions of this r, then we get, if we sum a bunch of them from 0 to infinity, then we get the following identity, 1 minus r. And we also get the geometric series. We can also easily get the value if we sum a finite number of them. So if we have n numbers that we're summing, then, yeah, oh wait, since I had an a there, yeah, a times 1 minus r. Okay, r to n. So we get 1 minus r to the n plus 1 over 1 minus r. And this is our value that we get from this series. Also, some other identities that are useful for similar calculations for discrete time, energy, and power. If we sum our index variable, so if we just sum n from 0 to infinity, then this gives us a identity k times, wait, hold on. This is not for infinity terms. This is, say, big N terms. Big N number of terms. Then this is going to be n times n plus 1 over 2. And we can also get the sum when we're summing n squared, the index variable. Same number of terms. This is going to be n times n plus 1 times 2n plus 1. And then this is going to be all over 6. Yeah, so these are two useful identities for calculating energy particularly. And now one trick that you haven't seen in the class is the following theorem, probably. So this is called the Tishmarsh convolution theorem. So this describes the support of signals that are convolved. So if we have if we have some signal that has some behavior, and it's support is from A to B. Yeah, so this signal from A to B. And we convolve it with some other signal. It doesn't matter what they are. It from C to D. These are both defined from A to B and C to D. Then the convolution of them is going to have the support A plus C to B plus D. So basically you can just sum these left endpoint, you can sum the left endpoint and the right endpoint, and this will be our bounds for our output of a convolution. And this is kind of useful when we do convolution problems, especially when we start using some of the identities that I just went over, the rectangle one particularly. But also this whole, if you have like an infinite, so let's say that D is infinite, and we have like a function that is going to go on forever, then this left endpoint is still the same. I mean, we can still sum the left endpoints, but the right endpoint is going to be all the way over here at infinity. So there's essentially going to be no right endpoint. Yeah, but yeah, this is pretty useful. As all it requires is us to just think a little geometrically and draw out the graphs of a lot of these. So right, let's see. So we're about an hour in, and but I'm pretty sure that the section has finished already. So if y'all are just getting here, then yeah, hi. I'm just been going over the midterm 1 material so far. You can catch the recording of this on YouTube. But right now, I'm going to be going over convolution, how you actually compute convolutions, and after that, I'm going to go over midterm 2 material, so Fourier analysis, Fourier series, etc. Right. So here, let's say we're convolving these two signals. So this rectangle function, yeah, standard unit rectangle, and this weird looking ramp thing with a box on the left and a ramp on the right. So so this is, if it isn't clear, this is 1 for everything less than 0, and it follows the behavior 1 minus t for 0 to 1. So how would I approach this problem? So the first step, I would say, is to break it up. Oh, shoot. Yeah, so I'm going to break this signal up. So I'm going to leave the rectangle alone. So this is 1/2 to 1/2. And I'm going to break up the right side, because this is kind of a weird function, and we don't know too much about weird functions like that one. So remember that we can use the distributive property. So we can also, this is technically linearity too, so it's because we can break up the left side behavior from -1. So that's 1. And we're going to sum that with that decreasing ramp. So the behavior on the right. So from 0 to 1, 1 minus t. Yeah, so prove to yourself that this and this weird one and these two, and the sum of these two signals is going to be the same. So yeah, this is great, because we can use the distributive property of convolution. And I'm going to write this out just in full so that we can see this. So we get this box convolved, standard unit box. This is going to be convolved with that shifted rectangle that we see over there on the right here. Let me just highlight this. Maybe that's not the best highlighting. That's worse. Okay, never mind. I'm not going to highlight it. Okay, so this shifted box, which is from -1 to 0, and also this is just 1. Notice that these are both unit boxes. And if we take the convolution of box, remember what that identity said if we convolve two boxes, then we get a triangle. But this triangle isn't going to be centered at 0. What I mean is that since this box over here, is shifted over to the left by half a unit, then our whole output is going to be shifted out by half a unit. So, or remember time invariance. Everything we're doing with convolution, we can always assume time invariance. So, yeah, and if we remember from the convolution theorem that I just went over, the Tishmarsh one with the bounds, we can just add these two values. So minus 1/2 minus 1, so that's 3/2. And this is the right endpoint is 1/2. And remember that for the standard unit triangle, this is going to have a resist to do that. So standard unit triangle gives us a maximal value of 1. So this will be the convolution of this left side. And what we're going to do is add this result to the convolution of our box. Remember, we're using convolved with the ramp. I'm going to take that. Oop, too far. From 0 to 1 minus t. Yeah, so we don't really have a nice identity for this one. So we're going to have to do our convolution algorithm. We're going to have to do all the integrals. And yeah, so this is the one that we're going to focus on right now. Because if we get this convolution, then we can sum together our results and then get our whole thing. Right. So first step. So if we have our two signals that we're going to convolve. So this one and this ramp. So choose the one that you want to flip and shift. So wait, hold on. I didn't actually define convolution real quick. So remember, if we have a signal x and h, should remember this from class. Then the convolution of them is going to be the integral over the entire support of x of tau times h of t minus tau d tau. Yeah, this is our definition of convolution. And notice that if we look at the h of t signal, we're flipping it. Since the variable we're integrating over is tau, where this is a flipped signal that is shifted over by the amount t. So, right. So we're going to choose which signal we're going to flip and shift. So the signal that we want to choose here is the one that's symmetric. So it's going to look the same across the right and left side of the y-axis. So it's going to be an even function. Those are typically the easiest ones to take care of this method. So I'm going to choose that one. So I'm going to choose this one. I'm going to choose that. And you want to rename the important point. So any boundary, any discontinuity, we're going to rename that in terms of t. So this becomes the t plus t naught axis, if you will. But this is just going to be, so what I mean by that is just add t to each of the endpoints. So if we look up here, minus 1/2 plus t is t minus 1/2. And then on the right, 1/2 t plus 1/2. Yeah, so great. So we have a signal here that is renamed in terms of t. So the next step here is to draw what I call the poses of the two signals. So every position that signal 1 that we're flipping and shifting can be with respect to signal 2. So in the case where both of them are bounded, so the left and right endpoints exist on both of these, so there's going to be 5 different ones. I'm going to write this, I'm going to draw our shifted signal in blue. So this is the one that's, maybe I'm going to use red. Been liking red today. Yeah, so that's the first one. And then here's the second one where the left is slightly over right. The left of the static signal is slightly overlapping. And then we're going to draw the case where it's completely overlapping. Draw my ramp. And box. Fourth one is where it's slightly overlapping, but on the right now. Pen. There we go. Slightly overlapping on the right. And then we do the last one where it's completely gone, essentially. It's going to be all the way to the right. And now, an important part of this method is to keep track of our endpoints. So we need to relabel all of these axes. So remember that our shifted function is now renamed in terms of t. So we're going to write in t minus 1/2. Wait. So this is t minus 1/2, t plus 1/2. This one is t minus 1/2, t plus 1/2. And before I forget, I'm going to get this one on the right too. So this is staying static, so it's going to be from its original bounds from 0 to 1, 0 to 1. I'm going to get this one, so it's from 0 to 1, from 0 to 1. Oh shoot, why is that 0? Why am I writing 0? That should be 1. 1, 1. And then let me continue with the red one. So t minus 1/2. These should be at the same. T minus 1/2. And then t minus 1/2. T plus 1/2. And then t minus 1/2. T plus 1/2. Right, so the next part of this method is to derive the bounds here. Right, so we have all of these different drawings, and now we can determine the bounds of our signal. We can determine the bounds of the different behaviors of our convolution by deriving the following inequalities from these pictures. So this one at top, notice that our red, so these are both to the left of everything. So this is the important points on our ramp are 0 and 1. So we have t minus 1/2 is less than 0, and t plus 1/2 is less than 0 also. So if we do some math, then we get t less than 1/2, and t is less than minus 1/2. Okay, so what do we do now? We have two inequalities, and they're both different. So what we do is we take the smallest region, or we take the largest region. So one of them needs to be true. Both of them need to be true. So this will be the smallest region. So we're going to choose this one. We need so this is the bound for when this pose is active, I guess. So this is going to be the bound here for case 1. I'm going to write case 1. Case 2. And then notice that now we have our right endpoint is going to be above 0. So let me write those same inequalities. So I was writing those in red. So 0 is less than t plus 1/2. and we have the left endpoint. We have the inequality that comes from the left one, and this is to the left, so 0 is less than t minus 1/2. So math, this is t plus 1/2. So if we combine those two, this means that 0 is less than t plus 1/2, and is greater than t minus 1/2. Right, so let's add 1/2. Wait, hold on. Yeah, let me subtract t. So let me put t minus t. So this is 1/2, and this one is negative 1/2. And let me multiply by negative 1 on all of these. So this is going to be from negative 1/2. So this is going to be the bound 1/2, because if we multiply times negative 1, then we get to flip the inequalities. So t negative 1/2. Right, so we have our bound here. Yeah, this is going to be our case 2. Our case 2 bound. Right, now case 3. So this one's a bit special. So notice that both of these functions are hitting the same point. So we can write out the inequality again, but this time it's going to be equality. It's going to be so t plus 1/2, and that's 1, and this left endpoint is going to be t minus 1/2. That one's going to be equal to 0. And now you can do some linear algebra and solve for t here, and this will give us t is equal to 1/2. So this case 3 is the max value. This is essentially the case that occurs whenever one signal is completely overlapped over the other. So get case 3. So this is going to be our cusp, if you will, of our convolution. And for case 4, the same thing. So 1 less than t minus 1/2, and this is greater than 0. So I'm doing the left endpoint right here, and then t plus 1/2. This is greater than 1. So let's do some math, and then we get that so 1/2 less than t less than 1/2. So this is 3/2. So 1 plus 1/2, and then t is greater than 1/2. So let's take the smaller of these two, and that's this one. So that's our bound for case 4. And then this is case 5. We're only worried about the region that overlaps between these two, if we remember. So I could derive the same bounds, but we already pretty much know the behavior here in case 5. So I'm just going to say, so for getting the bounds, I'm just going to take whatever's left, because this is the last one. So 3/2. Yeah, so we just took whatever was left of the real line. So great. Now I have a bunch of bounds for things, and now we're ready at this point to start doing integrals. I kind of like to stress that setting up the problem first is really the biggest part of doing these convolutions, especially for arbitrary functions. And doing this process, even if it seems tedious, will save you a lot of trouble, especially when you're first learning how to do it. So, right. So what we need to do now is derive some integrals. So the integral so each one of these cases is going to have its own integral. Yeah, so there's going to be one for each of them. Yeah, there's one for each of them. And it's going to be dependent on what regions overlap in our specific case that we're looking at. Yeah, so this one, there's overlap there. This one, let me draw it in blue. Or yellow. So this region's overlapped. This whole region over here is overlapped for case 3. This whole region over here is overlapped on case 4. The smaller one. And then there's no overlap on case 5. So we can already figure out some of our answer right now. Since there's no overlap on case 1 or case 5, as you can see, then we know that this integral, whatever it is, it's going to be 0. So this integral over here for case 5 is going to be 0, whatever it is, because there's no overlap. And now we just need to take care of these cases 2 to 4. Right, so how do we get that? So the integral is going to have, we're going to have to get the bounds from our picture again. We can't use these bounds that we derived. Those are for our final output. That's not for us yet. Right now, we need to take the bounds of this overlapped region. So notice that this yellow only exists from 0, yeah, because that's the left endpoint there where it's overlapped, and then it only exists from 0 to t plus 1/2. So the right endpoint of this yellow. So those are going to be our bounds for our integral. So from 0 to t plus 1/2. And then we're going to take the behavior of both of these functions in this overlapped region. So remember that this ramp is 1 minus t. Keep writing it wrong. And for everywhere is defined, this rectangle is 1. So we get 1 times the behavior of our static function, so 1 minus t. Multiply those, d tau. Oh wait, our integral is in terms of tau, so that's what I'm going to do it. Yeah. So if we do our integral here, then we're going to get some quadratic function. It's going to be like, so t plus 1/2 minus t plus 1/2 squared over 2. And you can check this integral. This should work out to that answer. Please let me know if it doesn't, if someone's checking me. And so this case, so I'm going to cover the case 3 in a second, but let's do the one for case 4 because it's very similar. So let's try and get the region where this yellow exists. So this is t minus 1/2, yeah, on the left, and then on the right is 1. So those are our bounds, t minus 1/2 and 1. So it's basically the same integral because the behaviors haven't changed. 1 minus t, yeah, they haven't changed even if we shifted one of the functions. So this is going to give us a very similar value. So this is going to be 1 minus 1/2, 1 minus 1/2, yeah, that's 1/2. And then this is going to be minus t minus 1/2 minus t plus, t minus 1/2 over 2. Yeah, these integrals are fairly easy just because it's a polynomial. But yeah, we should get something like that. If someone would simplify that you're great. But it's not necessary for the problem. But now we have all of our cases done, basically, except for case 3. So case 3 is one where we don't really have these inequalities, but there's the difference here doesn't matter. All that matters is that we have our yellow defined everywhere. So everywhere where our ramp function is defined, and also our box. So we can actually have the bounds 0 to 1. What I want to stress here is that since we have equality conditions, the output that we get in this case is going to be just a single number. Yeah, so our bounds on our integral are going to be just numbers instead of functions of t. dt. And this should be 1/2. I'm pretty sure. Yeah, that's 1/2. It's just the integral of this, and that's not too bad. So, right. So we have our answer here. This is going to be the output of our convolution. So just to write it out more succinctly, we have y of t is equal to, oh, I was calling it f of t and g of t, but yeah, let's call these f of t and g of t. This box and this ramp. Okay, great. Just making sure. Yeah, so we get from minus 1/2 integral 0. T is greater than 1/2, or t is greater than 3/2 is 0. Case 1 and 5. And then we get those two cases in the middle, and then we get a 1/2. So what this would look like if you were to draw out the function is that it's going to look something like, I'm going to say like this. I could be a little inaccurate there, where the maximum value is 1/2. And then everything outside of this, everything outside of 3/2 is going to be 0, and everything from negative 1/2 is going to be 0. And then this is going to have a maximum value at t is equal to 1/2. Yeah. So our y-axis goes here. Yeah. So that's it. That's our output here, y of t, of these two functions that we broke apart. So essentially, we got this. Wait, what was it, like this? Whatever it was. Well, anyway, you just add these two signals, and when you have it all written out, you should get something you should get the output by just cutting up both of these regions according to which ones have behavior defined in them, and then you'll sum the behaviors, and then you get your output. And that is kind of what I wanted to drive home here. By using these identities that I was talking about, the properties of convolution, you can simplify an integral that would be kind of hard to figure out otherwise. I guess you could probably figure out how to do this method of poses that I was talking about, where if you have multiple behaviors, but I wouldn't recommend it because I've never actually personally gotten it to work. This works because we broke it up into functions of single behavior in each of these functions, and it turned out to be pretty easy to do so. We can always do this, by the way. It's not like this is just some isolated case. We can always break it up into functions of different behavior, just because we always have linearity. So yeah, this is how I do convolution problems. And for this course, especially in the first exam, you're typically just going to be doing convolutions like this one. It's going to be fairly simple functions. You might have an exponential, you might have something that's unbounded on the right, but the same principles follow. It's just if we had something that was unbounded on the right, so if we, like, say we had our ramp, it was like a decaying exponential instead, and that is defined from 0 to infinity. So this method still holds. It's just that we would only have 3 cases then. These 4th and 5th, where the right side is overlapped, can't occur, just because it's going to be, there's never going to be a right side. It's just going to keep going on forever and ever. So This is for if it's unbounded. If we have bounded functions like we were talking about right here with our ramp and box, then it's just going to be 5. It's going to be 5. And yeah, this is how I would approach convolution problems. So, right, so this is essentially the material that's in midterm 1. That's really the main part is just going, the main part that would have been is just you would be computing like some energies, like taking integrals of the absolute value of your signal, absolute value squared. You'd be taking energies, you might be trying to figure out if a function is periodic, and we're going to do an example here right quick. And you would definitely have had a convolution problem. That's on every exam. And that's about it. Right after I solve a really quick example over periodicity real quick, just because there's for periodic signals that are clearly periodic, if they just have sines and cosines, essentially, it is really easy to get the fundamental period and the fundamental period of your whole thing, and to figure out if it's periodic. And I'll go over that probably now. Let me do that real quick. So let's say we had a signal x of t. By the way, if anyone can't see my pen, please let me know. I'm kind of assuming that everyone can kind of see what I can write. Sine. So let's say we have x of t, and this is going to be just say 1 plus cosine of 2t plus sine 4t plus e to the 6t, e to the j 6t, complex exponential. This complex exponential is always going to be a periodic function, just because we can decompose it into a cosine 6t plus imaginary number j, we're using j, sine 6t. Right. So this one's periodic too. So any sum of periodic functions is also going to be periodic. So the way that you do this problem is you take the omega from each of these. So this is omega, 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 and then you take the least common multiple of all of these. So 2, 4, wait, no, it's the GCD, greatest common divisor of 2, 4, and 6. And then this is going to be your fundamental frequency. This is going to be, so the GCD of 2, 4, and 6 is going to be 2, because 2 has a factor of only 2, because it's prime, 2 and 1, 4 has factors of 2 and 1 and 4, and then 6 has factors of 6, 3, 2, and 1. And notice in all of those sets, 2 is the common one. So yeah, that's our fundamental frequency. If we want to get our fundamental period, then this would just be, so t0 is 2 pi over omega 0. And this is going to be pi. And for continuous time signals, this is periodic. This is periodic. So what I'm going to illustrate right now is if we had a discrete time signal. So periodicity is a little different when we have discrete time, just because we don't have a continuum to work with. We need to have conditions on the fundamental frequency and period in order for it to be periodic, or else we'll have something that's almost periodic, but it's not technically periodic. So let's say x of n is the same signal, so plus x of cosine 2n plus sine 4n. And yeah, this is our signal. It doesn't matter if the last one is on there. So basically what you do is try and get the fundamental period and frequency as we did before. So the fundamental frequency of this one. So I'm just going to consider one of them, because the fundamental frequency of cosine, this cosine 2n, so I'm going to factor out 2 pi from this so that we can see. So if we write this in terms of 2 pi f instead of omega, then this is our f if we just factor out 2 pi, so 1 over pi. Wait, let me write that better. Okay, 1 over pi. Yeah, when you factor out 2 pi. So look at this f. So f is equal to 1 over pi. But in order to be periodic, so if we're periodic, if we have some signal x of n, then we also need x of n to be n plus n. So this looks very similar to what we had in continuous time. But this n here needs to be an integer. So this needs to be this needs to be an integer. It needs to be 1, 2, 3, 4, 5, 6, or negative 1, 2, 3, 4, 5, 6, so on. Yeah, but in order for that to happen, then we would need to have this fundamental frequency of this one cosine. This one, all of the components need to have a fundamental frequency which is rational. So it needs to be equal to some integers a and b, where b is non-zero. So this needs to be rational. So, but notice that pi is not a rational number, so we cannot say that this cosine here is periodic. And in order for something to be periodic, the sum of all of its components need to be. So this xn here is aperiodic. This one is aperiodic, even though it looks very similar to x of t here. Yeah, the one in continuous time. In order for this, so what? Now another question I'm going to ask right quick is this one periodic? X of n is equal to 1 plus cosine of 2 pi n. And I'm going to say yes. Yes, this one is periodic. Just because if we factor out the same 2 pi, this is, my professor called it the canonical form, I guess, of sinusoid in discrete time. So factor out 2 pi, so we get 1, 2 pi f, n. Maybe I should have written something other than 2 pi. I'm going to write 4 pi, just so it's more illustrative. 4 pi times 2. So that's our frequency now. So now that we have that, f is equal to 2. And this is a rational number. This is 2 over 1. So yes, this is periodic. And if we have a DC offset, this plus 1, it doesn't matter. This never affects periodicity. It's going to be periodic regardless of what DC level that we add. So yeah, this one is periodic because it has the pi in there. This one is not because it did not have the pi in there. And that's what I wanted to cover real quick. So yeah, that's essentially all of midterm 1, or what would have been. And yeah, getting into midterm 2, you should have gone over something called the convolution theorem, as your book calls it. So yeah, this should have been covered pretty soon after like your winter storm, if you're recalling. Why is my pen? Okay. Yeah, so remember, if we have x of t, and then we pass it through our system H, then its output, y of t, is going to be the impulse response of h of t, impulse response convolved with the input, x of t. So yeah, that's great, but one thing that's kind of annoying is that we get this convolution operation, and as we saw, convolution is hard. So one way that we can get around it is by looking at the frequency domain. So if we take the Fourier transform of the left and right, so that we're looking in the spectral domain, then we'll get, so the way we'd write this in the same system notation, so x of t passed through h, then this is going to be y, oh wait, hold on, not t, this is omega now, because we're in the frequency domain. Ooh. So this is going to be just the multiplication of the Fourier transform of our impulse response. Yeah, so h of t times, just multiplied, no longer convolved with our x of omega. Yeah, so this Fourier transform of the impulse response is called the frequency response of our system. And we denote it similarly to our input and output, as I did here, so h of omega. But this is the frequency response, and similarly to how we can figure out the output, we can always figure out the output given the impulse response, we can always figure out the output given the frequency response. And this lets us actually characterize our system more easily, just through its input and output behavior. Because notice that h of omega, since we're just multiplying these two spectrums, then we get y of omega over x omega. So you might actually encounter some problem that asks you to figure out what the system is actually doing, you know? So that's how you would, this is one way that you can figure that out. So I'm going to make a transition here, because now we're officially into midterm 2 material. This convolution theorem is essentially what bridges our time domain representation of signals and our frequency domain representation of signals. And for midterm 2, I usually have a different one, a different presentation that I give. So let me make sure that that's here. And y'all should be able to see that. Yeah, so this beam representation that I put together. Right, so exam 2. So this is essentially where you've caught up to at this point. It's going to cover Fourier analysis, and yeah, let's go ahead and get into it. So as we were talking about, Fourier analysis is going to be a bit different than our time domain representations, but it's typically not. The whole idea of it is not just for solving these problems. It's being able to understand and interpret systems and signals. And I'm going to talk about that with a bit of an analogy. So we know that Fourier analysis has a lot of math in there, and it might actually be a bit of a question, well, what does all of this mean? Why are we doing this? So your brain actually does something very similar to Fourier analysis, just in your head. And this is accomplished through your eardrums, your sound. This thing that converts the vibrations in the air, yeah, so these sinusoids that are hitting your ears, into something that you can kind of distinguish as what we call pitch a lot of times, frequency. Yeah, so when we talk with our friends, we say that something's high-pitched, like ah, and then low-pitched, like oh, and then and we have other ways to describe it. So like it's loud and quiet, like I just was. So these are both qualitative descriptors of sound. This Fourier analysis that happens naturally. And when we talk about Fourier analysis in class, we talk about the magnitude and phase spectrums. And these are just ways to let us talk quantitatively, with numbers, with precision, about the different frequencies of different signals that we have. So it might be the sound waves that we're talking about, but it also is much more general. We can talk about things in like communications. We can talk about things in vibration analysis, like if we were in mechanical engineering, but we're in electrical. So communications and like ripples of things. anything that has regular behavior typically has some kind of insights in Fourier analysis. So, right. So I'm going to talk about how the magnitude spectrum and the phase spectrum are tools for understanding. They're tools for understanding what a signal is doing. And getting on that, the magnitude spectrum is just, it tells us the amplitude of different frequencies in a signal. So what do I mean by frequency? Just a sinusoid that is defined with the same angular frequency as each point in the x-axis. So we remember from math that any function can be represented as a sum of sines and cosines, or an infinite sum of them. Yeah, just to kind of really hammer home that fact in case you haven't seen it before, I'm going to look at this. This should be a square wave, and this equation over here is the Fourier series of a square wave. So what do I mean by a square wave? Let me just draw it right quick. It's like box, but there's another box, and there's another box. And you'll see these a lot, especially if you work with digital signals. So, right. So this is just starting out with a single harmonic. So this is just with one sinusoid. N is one sinusoid. But what happens when we increase that? Notice that as we increase the number of n, then we get something that looks a lot more like our square wave. And as we continuously increase that number up to infinity, I'm not going to because that's going to explode my laptop, but yeah, we'll get a square wave up to something called Gibbs phenomenon, but I'm not going to go into that right now. So yeah, this tells us so we can decompose everything into sines and cosines. Great. So magnitude spectrum is where we talk about how loud each of those sinusoids are. So yeah, that's what we got. Some of the properties of it are that the magnitude spectrum is always going to be non-negative. We always know that we're talking about the magnitude spectrum if we have this absolute value signs. Those are what denote the magnitude spectrum of some spectra z of omega. So it's always non-negative. And for purely real signals, like we're often working with, so we'll get something called conjugate symmetry. So essentially what that means is that the left and right sides of this magnitude spectrum will be symmetric. It's going to be an even function. Right, so the magnitude spectrum is going to be the focus of what I'm talking about here, just because it's typically the most important one for designing systems. I'm not saying that the phase spectrum should be ignored, just because if the phase spectrum is what guarantees uniqueness, it's what guarantees that we can exactly figure out which system we can exactly derive like a system using both of them, whereas if we just had one alone, we wouldn't be able to say much about it. But yeah, the magnitude spectrum is typically when we talk about designing like interpretable systems. This is one we're concerned with. So if we remember that LTI systems can be characterized by their impulse response, so the output can always be predicted from the input. Yeah, so if we have our impulse response, so we get, say that z of t. Yeah, the frequency response is how we can characterize the behavior of a system. Yeah, so this is just the Fourier transform of our frequency response. Or our frequency response is just the Fourier transform of the impulse response. When we get an impulse in, well, what do we get in the output? It's just the transform of that. And yeah, so yeah, when we talk about design, we're typically talking about things like bandwidth. So how wide this spectrum is. Like this one right here is defined for all omega, all frequencies, but we can have spectra that look like a box, like we were talking about. We love boxes. And yeah, we can also specify things like, well, we want it to be, say, like 1/2. Well, we want frequencies of 3 to be 1/2. Those are things that you might hear when you talk to other engineers. But yeah, bringing us to the phase spectrum. So what this means intuitively is how different frequencies are offset in time with respect to one period. So like if we have a sinusoid that is, remember, if we have a periodic function, if we shift it over by one period, so if we shift it over by one period, then we get exact copies at each time. Like it won't change if we shift it over one period or any multiple of periods. But how about if we didn't shift it over by a full period? What if we shifted it over by half a period? So this signal would look a bit different, actually. Let me draw it on there in a different color. Yeah, so can we say that these are the same signal if the phase is off? No, and what this phase spectrum tells us is how these are going to interact with each other if we were to sum them up. So for some phases you might get positive interference where it actually increases the amplitude, and other ones it might give you a case where it just turns everything to zero. And this happens independently for each one of these frequencies. Each value in the domain this happens. So this phase spectrum is just how we summarize all of this information. Yeah, so it tells us how they're offset in time. And these values are bounded from pi to pi. Yeah, negative pi to pi. Just because we're only concerned about offsets within one period. And yeah, they tell you how they interact. And a similar conjugate symmetry phenomenon occurs for real signals. Remember, they have to be real. Where the diagonal, essentially, if we reflect across the y equals x line, then we'll get the same thing on both sides. Yeah, so it's an odd function, by the way. That's what you call it. Yeah, so right, so we have the properties here of, yeah, just summarized. If it's odd, if we have an odd function it's real, then our frequency spectrum is going to be odd and imaginary. It's not going to have a real part. And if we have the signal being even and real, then it's going to be having a even frequency spectrum. And it's going to be real only. It's not going to be imaginary. Those are the two. And that might be like a bonus problem. Yeah, so I've talked a lot about the Fourier transform now. It's been how long? Yeah, I haven't used that app before. It doesn't tell me the time. But yeah, so this is, I've talked quite a bit of time about Fourier transform, but I haven't actually defined it yet. So here's the definition. It's a integral transform that maps a complex function to a complex function. But so in full generality, this can be a complex function, but often we're considered real functions just because we often don't think in terms of complex functions unless we really need to be. So yeah, if we take the integral from negative infinity to infinity of f of t times this weird function, the complex exponential, yeah, the inverse of it, then that gives us our Fourier transform. So this is sometimes written f of omega if our function is f. And yeah, so we can also invert this transform. So we can go from a frequency spectrum to the time domain with this integral. So we can go backwards. So the inverse Fourier transform is defined as, so multiplied by 1 over 2 pi if we're using omega, times the integral from negative infinity to infinity of our frequency spectrum times the complex exponential, but now not inverted. And this is integrated with respect to omega. Yeah, the forward transform was defined in terms of the integral with respect to t, time. We're integrating out t, and the inverse one is integrating out omega. Yeah, so what these two integrals, typically you won't be programming in, you typically won't be implementing these two integrals yourself. What we have is that we usually just have some function, some set of data in like MATLAB or something, and then we pass it to some function that will perform this transform for us. And then we can take the output there. That's going to be a complex function. So we get the complex valued Fourier transform, the spectrum. So remember that any complex number can be written as the sum of a plus jb. But the one that we've been talking about most here is the magnitude spectrum, so this coefficient term, and this phase spectrum, this angle of our frequency spectrum. Right, so yeah, that's how Fourier transform usually works whenever we're out like building. So right. So these are very important ideas just because they let us interpret the transform, or this lets us interpret our time domain function in terms of these frequencies, the pitch, the orthogonal components. And that this can give us a lot of good results. It's very interpretable. Yeah, so like I went over, the link between the time domain representation of signals and the frequency domain one is the convolution theorem. So if we if we take the Fourier transform of the convolution of two signals, we get the multiplication of our input and the other function. Yeah, so this is we have something called duality, where like if we have something in the time domain, we'll probably get something similar in the frequency domain, and vice versa. If we have something in the frequency domain, we can get something in the time domain, some result. So yeah, this is that right here for the convolution theorem. If we take the inverse Fourier transform of a convolution, then we get the multiplication of signals in time domain. And yeah, one second, I'll be right back. Take a quick break real quick. Woo, this is a long review. Alright, so getting back to things, we have the duality principle of convolution theorem. So if we get if we have a signal and we take the Fourier transform of it, so we have x omega, we can there's a lot of useful properties for us when we're solving problems. So yeah, if we time shift in the input, if we time shift the time domain representation, then we'll get the same Fourier transform, just multiplied by just a number. It's just going to be a complex number, proportionate to the time shift here. Yeah, notice that we have the same tau. Yeah, so that's our time shift property. We get time scaling. So essentially we get, so if we were to shrink something in time, So we're making it faster. Then we get the inverse in the Fourier domain. So we get a stretching of so we get a stretching of our spectrum here, just because it's divided by some number. And just to make sure that the energy stays the same, then we'll divide it by a. Yeah, so don't forget that multiplied by 1 over a if you use this property. So that's time scaling. And we also get a similar linearity property for the frequency domain representations of two signals. So remember, if we have ax plus b, if we take the Fourier transform, then we get a similar ax plus y, yb. And yeah, this linearity property is really useful because it lets us kind of compose and decompose frequency domain representations similarly to what we have for time domain ones. Yeah, so we can, our block diagrams will stay the same no matter if we're in the time domain or in the frequency domain. And one theorem that's pretty important is Parseval's theorem. So this is essentially a theorem that it tells you that energy is what we call unitary. So the way I like to think of something being unitary is money. So if I go across it, so if I take $10 and I go across the border to like Canada or something, it's still going to be worth $10 in USD, but it's going to have a different value. It's going to have a different representation in terms of like Canadian dollars. So, but we can always get back and forth between the time domain and the frequency domain. Yeah, that they will have the same amount of energy, effectively, up to this multiple of 1 over 2 pi. Why is that a line? Why is that a line? Okay, yeah. Yeah, so it's up to this 1 over 2 pi. If we integrate, if we take the energy, it's going to have the same effect as if we took the energy of this, it's going to have the same amount of energy as if we took that integral across the frequency domain, up to this factor of 1 over 2 pi. Right, so, yeah, if we have, so there's a few more properties that are important for the Fourier transform. So, the first of which is, the first that I'm going to go over, at least, is taking the derivative in time. So if we took dn, yeah, of our signal x, then the spectrum will have, it'll be the same one, just multiplied by a complex number again, like similar to how time shift happened. It's just going to be the same spectrum, but it's going to have some other factor. Yeah, so essentially this would mean that like if we had like something like that, it would kind of turn it into a ramp. It's kind of hard to describe right here, and I don't have this explanation prepared very well, but yeah, that's the time derivative property. It turns it into, it essentially just tilts everything up, and but this derivative is, it can be talked about the order of like a filter or something. So yeah, we get a similar property if we integrate in time. So if we take the integral from 0 to t, from negative infinity to t. Yeah, it's not from negative infinity to infinity, because that just gives us a number. But if we have a signal that's just the integral over time, the causal integral, yeah, where we're just taking the area of a function over time, then the Fourier transform of that is going to be a very similar one, where we divide by this j omega term. Whereas if we took the derivative, we multiply by it, we divide by it for integrals. And then we add this DC offset term, essentially. This is just going to be a delta function, so a scaled delta function. So remember, it's a spike. And then it's going to have the value of pi x0. So this DC value, yeah, this, and it's going to be added to whatever the scaled spectrum is. Right. So that's the property for taking integrals in time. And we through duality we get a similar result for time, or for the frequency domain. Whereas if we took the derivative in frequency, then we get multiplication by t in the time domain. Yeah, and just remember that like if like I'm going to give a similar argument to what I was giving before for the derivative property. It's like if we had this ramp, if we had this box, then we multiply it by t, and we actually get like a ramp that's going up. Like, so yeah, think of it like we're rotating our function almost. But yeah, that's the property that we get if we multiply by t or take the time derivative, or take the frequency domain derivative. Right. So the Fourier series. I like to talk about the Fourier transform first, just because I think it's more illustrative. You get a better idea of what's actually going on here, especially for signals that we work with typically. Because we won't really have an infinite time signal like we would hit in a periodic signal. But it's important nonetheless. So the Fourier series. So if we remember that the complex exponential is just the sum of this cosine and the sine. Yeah, complex sum. So this gives us a few ways to write the Fourier series. There's several equivalent forms that they talk about in course. Is that we can write in terms of exponentials, so the exponential forms. So yeah, the exponential form of the Fourier series. Right. So this is just going to be a weighted sum of complex exponentials. So we also get a very similar form through Euler's formula, the trig form, which is essentially just applying this identity here to this one. Yeah, it's pretty simple proof if we get into the details. I'm not going to, but this is something that I think you could do if you're really interested. So we get the trig form here. It's a sum of sines and cosines. And another result that we get here for purely real signals is the compact form. This essentially lets us drop out this sum of sines and lets us add a phase term to cosines. And this is useful if we want to, like, say, plot the Fourier series, like I did in the first when I first started talking about this. So yeah, you'd use the compact form there. Also, these terms in front here, A0 and C0, those are just going to be your DC offset. So what do I mean by DC offset? I keep saying that term. So if I have a signal x, which is just a sinusoid, then if I add a DC offset to it, I'm just adding like a value. So our x of t is up here, but we added some a, and this one was 0. So yeah, that's essentially what I mean by that. Right. So yeah, so we have all these forms for Fourier series, and there's actually a lot of relationships. Well, we can actually derive the coefficients from one form from the others. So these are all basically the same thing. It's usually just an application of Euler's formula. But so whenever we get a Fourier transform problem, or whenever we're trying to get Fourier series coefficients, I would say the best way to do it is it's really just looking at it by inspection. So if we have like cosines and sines in our function, if we know that it's periodic, just because like say x of t is just a sum of like cosine of like 2 pi t, and then plus sine of forward phi t. Yeah, then we'll just want to get a, so I guess consider this an example, because I'm going to keep going with this one. Yeah, so how I would do it right here is to use these formulas here. So 1/2 j omega plus e to the j, e to the minus j omega, and then a similar one for sine. So instead of, wait, this should be minus. This should be a minus. That's an error there. Yeah, so we subtract the two complex exponentials, though, on top. This should be a formula that you might remember. So yeah, I'm just going to break this up into complex exponentials. So j omega, wait, so j times 2 pi t plus 1/2, still on the cosine, e to the minus j 2 pi t. And then we get the sine. Now I'm working on the sine. This is sine 1/2j of e to the j 4 pi t plus, no wait, it's minus. That is the error that was in the slide. E to the j 4 pi t minus. Right, so we get this sum of exponentials. And what did this look like in our first, what did this look like? This was our exponential form of the, this was our exponential form. So we can get, yeah, this is just, so notice that each of these is just a multiple of 2 pi. So we get, so like notice like 2 pi, negative 2 pi, 4 pi, 4 pi, 4 pi, negative 4 pi. Those are all multiples of 2 pi. So we get our fundamental frequency, omega 0, is 2 pi. Yeah, straight out the gate. So we get that, and then, yeah, so we can write the sum of Cn is equal to e to the j omega 0 times t, times n. Sum of complex exponentials, where Cn, so this is times 1, so C1 is equal to 1/2. So this is the coefficient in front of this 2 pi times 1, times 1. Yeah, wait, let me write it like this. Let me write it here. So 2 pi times 1. This one is 2 pi times negative 1. This one is 2 pi times 2. 2 now. And then this one was 2 pi times negative 2. Yeah, so we get our coefficients now. So C1, C2 is equal to, so this k value, so 2 pi. 2 pi times 2, k value is 2, so 1/2j. And C negative 2, because we get this one, is equal to minus 1/2j. This is just the coefficient in front here. And we get C negative 1 is equal to 1/2. Yeah. So, yeah, this is how I would do this one right here. I always turn it into exponential form. If you're smarter than I am, then you would have noticed that this function right here was already a sum of cosine and sine. So this is technically already in the trig form. So like that, like a0 would have been, so a1 would have been a 1, and then b2, because this is 2 pi times 2. This one would have been what? This would have been 1 also. And then all the rest of them would have been 0 for both of these cases. So yeah, this is how I would do a Fourier series problem if we have sines, cosines, complex exponentials. This works by inspection. But yeah, so if we have the Fourier series in one form, so we have the exponential form first. I really like that one. So yeah, let's say we have that one first. We can actually turn the complex exponent. We can actually turn the trig form. So let's say we have the trig form and we needed the complex exponential form. Yeah, we needed the exponential form. And then we could actually derive that. Let's see, there's a mistake here. Yeah, I think this one is minus. Yeah, I think it's minus n. Yeah, c to the minus n. Yeah. Yeah. So these are the formulas. And then if we had the exponential form and we want to get the trig form, then we just take twice times the real part and then twice times the imaginary part, or the negative of that. Then we get the trig form. Notice that a0 is equal to c0. Like the DC offset term is going to be the same. And you can get it easily from the exponential form. That's kind of why I really like it. Just because if you multiply it by 2 and take the absolute value, and then you take the angle of it, so if we have a complex number a plus jb, then so let's call this z. So then the angle of z, arc z, is going to be the arctan. So arctan of b over a. That's what I mean by the angle of it, just so that we're very clear. Yeah, so let's see. So yeah, one thing that I'd suggest is try to avoid doing integrals whenever possible when you're trying to get Fourier series coefficients. So yeah, these two formulas here are pretty helpful if you do have to take this integral. So you're not really going to be able to do it by inspection if you have like something with discontinuities, like a triangle or a square, a sawtooth, like something with where things aren't smooth. So yeah, so these two formulas are helpful in those types of integrals sometimes. So yeah, if we take the exponential form, the complex exponentials, or the coefficients for the exponential form are going to be this integral here. So we're going to multiply this x of t times this inverse of the complex exponential and omega t. So, and this is just from 0 to t. So this is what you call the inner product for the two functions here, e to the j and omega naught t. If you've ever heard that language in another course, maybe linear algebra. So yeah, and then this is just scaled by t. Yeah, so that's going to be your Fourier coefficients for all n. You just essentially do one integral if you can. Don't try and split it up into different values of n if possible. And then for the trig forms, the formula that you'd use is this bottom one here. Yeah, so this an, the real part, the coefficient for the cosines are going to be 2 times the very similar integral as before, but instead of this minus j omega naught t, e to the j omega naught t, then you get this cosine. Yeah, that's the only difference between these two. And then you multiply it by 2. Yeah, it's always twice. No, don't forget that 2 factor. Yeah, so, and then we get a very similar integral with sine instead for Bn, the coefficients for the sum of sines. Right, so the Fourier transform and Fourier series are talking about very similar ideas. It's just one is for aperiodic signals essentially, and the other one is for periodic signals. But they still both give you a more interpretable representation of a time domain signal that might look just something like garbage. Like you might not actually have any idea what it looks like, when you look at it in the time domain. But if you look in the frequency domain, this might actually look like something that's a lot more reasonable. It just might be like a bunch of delta functions, especially if it's periodic. Yeah, if it's periodic, it's going to be a Fourier series. It's going to have a Fourier series, and it will just be a sum of deltas. But anyway, yeah. So like I said, so for periodic signals, it's going to be discrete in the frequency domain. We can plot out the different values of ck. Yeah, the different coefficient values. Just because remember that the Fourier transform of a delta function, yeah, or the Fourier transform of a complex exponential j omega t is going to be a delta function that's shifted over, so omega minus omega naught. Yeah, so let's see, and you can get that from the time shift property, but I'm going to go over some of the common transform pairs before we start going over some computational examples. So the Fourier series is going to be discrete in the frequency domain if you plot it. If you plot it out, discrete. And for aperiodic signals, then it's going to be continuous in the frequency domain. And there's actually a little bit more of a connection here. You might actually see right now, but these two, you might actually see right now if you notice that both of these signals look kind of similar. But that's for the last exam when we talk about sampling. Yeah, so right. So a few of the common Fourier transform and Fourier series that are going to be useful for you when you're solving problems, just like as identities. Like these are things that you should probably memorize. Are the following. Right. So we get the complex exponential, like I was talking about. So if we have the complex exponential, which remember is a periodic function, then we get a single spike in the Fourier domain. Yeah, so it's going to be centered at omega naught. It's going to have, that's where its one value is going to be. So if we have a cosine, remember that formula that we talked about? So cosine is equal to just e to the omega naught t plus e to the negative omega naught t over 2. Right, so this is going to give us two spikes in the frequency domain. So this is centered at omega 0 and omega naught. Omega naught. Yeah, it's going to be symmetric. And so this is the magnitude spectrum of cosine. And the phase spectrum is going to be 0. Phase cosine is equal to 0. It's just going to be right. So we get that one for cosine. And if we have sine, we get something that looks very similar. So it's going to be, so we're going to get two spikes in the magnitude spectrum again. So sine, so this is the magnitude spectrum of sine, and this is centered at omega 0, omega 0. But it's going to have a phase spectrum that looks a lot different from cosine. It's going to have phase spectrum values that, so the angle, so phase spectrum of sine is going to have spikes at omega and omega naught. So these are going to be at 90 degrees and negative 90 degrees at the same values in frequency. Yeah, so those are the transforms that you get there. Oh yeah, these are multiplied by pi. Yeah, so, and also an important one to note is the Fourier transform of a rectangle function. So you'll need to know the forward transform of the rectangle in the time domain, and also the transform, and also the reverse of it in the frequency domain. Just because rectangles are very common for engineering purposes. So let's see. So if we have the time domain signal, That's a box. Standard unit 1/2, -1/2. This gives us a sinc function. So this is going to be blue. It's going to look kind of like that. And it's going to have the zeros be at multiples of the period. So basically it's going to be pi over 1, pi over, so 2 pi over 1. And I'm writing the over 1 here because we could actually replace that by a rectangle with a different period. So this is t. Then, yeah, the zeros would be at multiples of 1 over t. Yeah, and then, yeah, so this is valued 1 there at the top. And also, yeah, what else could I say about that? Anyway, that it might come to me later. Yeah, so that's Fourier transform of a rectangle. And then, yeah, for the delta function, if we take the Fourier transform of that one, so if we have this one in the time domain, then this will give us a value of 1 for all frequency. Yeah, for all frequencies, it's just going to be a value of 1. So this is what we characterize white noise as. If you go farther in signal processing, this is, yeah. So this is what we would call white noise, but this isn't really possible in real systems. I don't know. Take more courses. Yeah. So we got. Yeah. So if we have a delta function and then we take the Fourier transform of it, it gives us 1. But actually, if we get the Fourier transform of a infinite sum of them, then we're going to get an infinite sum in the output. No, this is something that I still really haven't convinced myself of, but this is just what the consensus is. So yeah, if we just have a sum of delta functions, yeah, just an infinite sum, then we also get an infinite sum of deltas in the Fourier domain. And these are all regularly spaced. So yeah, these are all going to be spaced apart according to 1 over t. And this, where if these are spaced out according to t. Yeah, so that's something that we call the comb, the Dirac comb, or maybe the Shaw function, or whatever names people have for it. But yeah, this is quite a bit different than if you just have a single delta function. So this is something that you just need to remember. Right, so now that I've given you most of the tools that you need to be solving problems, let's go ahead and start doing some of that. Yeah, so let me check the time here. So we have about 30 minutes left, 40 minutes. So we can go over a few problems doing Fourier series. So let's see, let me go through my notes real quick. Yeah, so I guess like one thing that I guess I should cover is just how do we derive the Fourier series, and then take the inverse. I think that's probably something that might be helpful, I guess. Let's see. Yeah, so if we take the signal x of t, and let's say it's just like this. Let's have x of t is going to be a cosine of t. No, wait, that's sine of t. Yeah, this is going to be sine of t. For t from pi to pi. From t to 0 to pi. And then a 0 everywhere else. So I'm going to take the Fourier transform of this one. Yeah, so just x of omega is equal to the integral of, so from negative infinity to infinity of x of t times e to the j omega t dt. Right, so this is going to be the integral from 0 to pi of sine of t e to the j omega t dt. And this is a, let's see, I'm going to break this up right now into two functions right now. Let's see. Because remember that the complex exponential is just a sines and cosines, sum of sine and cosine. So let me try and move some of this right quick. Okay, well, yeah, it looks like we're going to go back and forth. So from 0 to pi of sine of t times cosine of omega t dt, and then plus j times the integral from pi to 0 of sine squared t dt. So remember those identities that I was talking about. So remember that this one, sine of squared of t, is going to be 1 minus cosine of 2t. This comes from this double angle formula squared over 2. So yeah, we'll substitute that here in a second. And then, yeah, this sine plus cosine term. So I'm pretty sure that this comes from this also comes from a trig identity. So we can take, so this would be sine of 1 plus omega t times, or plus, I think, sine 1 minus omega t. Yeah, because I think you can sum these two if it's sine and then cosine, and then subtract it. Yeah, but anyway, it's going to look similar to this one. So that's your identity, or this is one that I'm going to roll with. Please correct me if I'm wrong. So yeah, so we get 0 to pi sine. This is going to be, let me clean up a bit. I'm going to switch back to OneNote after this. This is not where I'm going to solve problems after this one. Yeah, so 0 to pi sine 1 plus omega t dt plus this other integral of the sine 1 minus omega t dt plus the integral from 1/2 times dt from 0 to pi plus cosine plus the integral from cosine. So minus cosine 2t over 2 dt from 0 to pi. Yeah, so I'm going to solve all of these integrals, and yeah, so if you solve all of these integrals, let me just go ahead and write the answer. This just a bit of computation. Should have been something from calculus, but you'll get the following Fourier transform. Oh, what? Yeah. So 1 over 1 minus omega. 1 minus omega sine 1 minus omega pi plus 1 over 1 plus omega sine 1 plus omega pi. Right, so this is your Fourier transform here. And yeah, this is just a matter of solving all 4 of these integrals, and then you'll get a function of omega. Make sure that it's a function of omega, not of t. There should not be any t's left in our Fourier transform here. But yeah, that's great. Yeah, for the sake of time, I'm not going to do these integrals. So yeah, let me switch back here just because I find it more comfortable. But anyway, so let's actually try and use that convolution theorem that I was talking about. So let's try and do that. So let's say we have x of t, and we're passing it through a h of t. Yeah, so let's say we're passing it through a function h, and we get y of t. And then this h is going to be defined as, so h is going to be, I'm going to draw it like this. So it's going to be this is talking about the internals of h. So h is going to be, say, the derivative of in time, and then we're going to multiply it by a sinc of t. Yeah, so, and then we get our output. So this is y. So how would we do this problem? Right, so let's figure out. Let's say we're given x of t is equal to a delta. We're trying to get the impulse response. And yeah, so what's the impulse response here? So remember that because of linearity, we can get the Fourier transform, or no, because of the convolution theorem, we can represent the same h in the frequency domain. So yeah, we can write this as x of j omega. Yeah, so times j omega. That's times j omega, and then the spectrum of a sinc function, remember, is a rectangle of t, or rectangle of omega. And then this is going to give us the frequency domain. So our full system would be written as x omega into, so we multiply it first by j omega, and then we multiply it by a rectangle, and then we get our final output y of omega. Just because, remember that passing anything through here is taking the, is just multiplying it by a whatever the impulse response of each of these is. So, and this is a bit easier than doing the convolution here, because this d over dt, you have like a formula for d over dt. There should have been, he's talked about it, Dr. Park, in his course, and we would have to convolve that with a sinc function, and that's kind of annoying. So yeah, we get x omega, and then we multiply it by j omega, because we're taking our derivative, and then we multiply it by a rectangle omega. Yeah, so this is just going to be, let's say, here. Yeah, so this is just going to have, yeah, so 1/2 and then 1/2. So yeah, our output spectrum here would just be a, so we get y of t, or y of omega. Our output spectrum is going to be just all of these things multiplied together. So let me write it out right quick. So y of omega is equal to j omega times the rectangle of omega times x omega. Right. So so we have the frequency spectrum right now. So what about if we wanted what if we wanted the time domain output here? We're wanting this one. Uh, yeah, so we're wanting the output here. So we just have to take the inverse Fourier transform now. So this is going to be, so remember the duality for the taking the j omega times a function x omega. So we get y of t is equal to the inverse Fourier transform of all of these things. J omega rectangle omega times x omega. Yeah, so yeah, we'll actually get something that, so I'm just going to keep writing this inverse Fourier transform. So we get of rectangle omega times dx over d omega. Because if we take these two and take the inverse, then we get the derivative of our time domain signal. Because remember that frequency differentiation property. Yeah, so we get the time domain derivative, and then we get, a sinc function. Sinc omega of dx of dt. Let's see. So yeah, now we have the output of our function. Let's see. Yeah, let's see. Let me try and get a better problem. So that's our output. Yeah, let's see. I don't know. Does anyone have any requests in the Discord chat? Yeah, if not, I have a problem here. Let me try and get this together. Yeah, so let's say we have like a periodic signal. Let's say we're given a periodic signal, and then we want to get the spectrum of it. So we want to get the Fourier transform, or we want to get the Fourier series. And this is going to be 1/2, and then these are going to be -1/2. And then this is going to be spaced out according to the integers. So 1, this one's 2, this one's 3, this one's 4, 5. And then we got -1, -2, -3. Let's see. Let's move that. -4. Yeah. So that's our. Let's say you're given that, and then we're trying to get the. We're trying to get the spectrum of this one. So since this is periodic, the Fourier series. So let's try and derive this one. So let's get. Remember that the Fourier series coefficients formula. So remember Cn is going to be the integral 1 over t from 0 to t of x of t times e to the negative j omega naught t nt dt. Yeah, that's our formula for taking the Fourier series coefficients. So I'm going to box this in red. Oh, there we go. Because this is what I'm going to use right here. Remember that rule I said, where if we have a periodic signal with discontinuities, then we're going to want to pull out this formula instead of trying to look at it by inspection. I already showed you the case where if it's a sum of sines and cosines, then you do it by inspection. So yeah, we're just going to basically be doing these integrals once we can actually figure out how to apply this formula, because this is all that you're given basically. Okay, so the first order of business is, well, you need to figure out what omega naught is, and also what this t value is, because you won't be able to apply this formula without those. So make sure that, so if we look at our signal here, notice that if we take this section here, so this section from -1 to 3, let me try and clean this up a bit. Clean this up. Yeah, so from -1 to 3, notice that if we move this over by like 4 units, then we're also going to get the same exact signal. Yeah, but this time it's going to be starting from 4 to, yeah, it's going to be starting from 4 to 7. No, wait. Yeah, 4 to 8. 4 to 8. And it's going to include this space here, and it's also going to include the space here. Yeah, it should be from -1 to 4. That is our signal. So our period is going to be 5. So we should actually get a full period of our signal over at 9. Yeah, this is just kind of something that you have to kind of look at the signal and try and determine how far can you shift it to where you get to copy. So that's how you'd figure out that the fundamental period is going to be 5. And now we need to get the fundamental frequency. So remember that remember this formula. So we got omega 0 is equal to 2 pi over t. So it's 2/5 pi. Yeah, 2/5 pi. Yeah, so now that we have both of those numbers, we can actually apply this formula that we just pulled out right there. Okay, so Cn is equal to 1 over 5 from the integral from 0 to 5 of x of t e to the negative j omega naught. So omega naught is 2/5 t, 2/5 pi t times n dt. Right. So since this signal that we're given has different piecewise behavior within a bunch of different regions, so like notice from 0 to 1, it's this like 1/2. Yeah, so let's try and write out what exactly it does within one period. That'll help us figure out what to put here in place of x of t in our integral. So from -1 to 1. Yeah, so from -1 to 1/2. From -1/2. This is going to go up to yeah, so this is t plus 1. Pretty sure? Yeah, so this goes up to t plus 1. And then this is, yeah. And then from here, from 0 to, no wait, hold on. Let me backtrack a little bit. I drew my thing a bit wrong. Yeah, so this is 0. So this is actually just from 1/2. So t plus 1/2. Yeah, so 1/2 t plus 1/2. And then minus 1/2 t. Minus 1/2. From 0 to 1. Let me summarize this here. X of t. So over 1t. So we get from so 1/2 t plus 1, and then 1/2 1 minus t for t is less than or equal to 0, 1, -1, then t is less than 1, 0. Right, so that's this one over here, this main lop. And then notice that it's 0 from 1 to 2. And so we've taken care of that one. Let me just highlight the ones that we've already taken care of. So highlight means it's done. 0, 0, t, 2, 1. Okay, great. And then we're going to take care of this region here now. So we get this one. So 2 minus, so from 2, this is going to be to -1/2. So 2 minus, so 0 minus 1/2, so 1/2 over 2 over 3. Wait, let me look at my problem. Yeah, so I made a mistake. This one's supposed to be periodic, so this one's actually a 4, 3, 5. Wait, so does that change our fundamental period? It does. Yeah, so it's 6. Yeah, so it's -1 to 5 is 6. So this would give us, yeah, make those edits. 6, 6. Then this would be 1/3. 1/3 pi. Pi over 3. Okay. Yeah, so we get all that. Wait, 6, 6. I'm just fixing my mistake that I said the period was different than it is. Yeah. Okay, so that makes more sense. Okay. And then we get, so now I'm trying to get the behavior for this region, from 2 to 3. So I'm just trying to figure out what the line is here. So if we go up, so this has a slope of 1/2, 1/2, and then 1. Yeah, so this will go up to 1. So 3. So this has a slope of 1. And then this is going to go up to 2. T plus 2. 1/2. Yeah, okay. So from 3 to 2. And then we're going to get something similar as we got over there. Minus, so this is going to be probably 2 minus t over 1/2. Yeah, okay. So I'm pretty sure that should be right. So we get from t to 3 to 4. Yeah, so this is our function x. And apologize if there's any mistakes. So this is from 0 to 4 to 5. Yeah. Or t from 4 to 5. Right. So this is our x of t. Finally figured out what this is actually doing within one period of the signal that we're given. So yeah, if we apply that derivation to our formula, then we're going to get a series of 6 integrals. Oh wait, hold on. This needs to be within a window that's within one period. So since we derived the behaviors from 1 to -1 to 5, I'm just going to change those integrals. It just needs to be the same length. So this upper limit needs to be, this upper limit minus the lower limit must be the same thing as t. It doesn't actually matter where we take this integral over, as long as we're doing it over one period of the signal. So, right, so 1 over 6 times, let me just move this over. Okay. Move, oh, too far. Okay, yeah. So the only things that we have to take care of are these regions where it's non-zero. So let's write out the integral. So -1/2. So from -1 to 0 is going to be 1/2 t plus 1. And that's going to be from times e to the negative j pi over 3 times t n dt. And then we get the sum of from 0 to 1, from 1/2, 1 minus t, e to the negative j omega over 3 t n dt, plus, this is just me rewriting what the behaviors were. So from 2 to 3, I'm skipping the one that was 0 for that whole chunk in the middle, t plus 2. And then we get e to the negative pi over 3 t n plus integral from 3 to 4, -1/2, 2 minus t dt. Oh wait, dt, what's that one? E to the negative j pi over 3 t and dt. Okay, yeah, so we have a bunch of integrals that we gotta solve. And then, yeah, so let's see, we're kind of running short on time. So unless anyone has any other problems to suggest right now, I'm just going to end up I'm just going to spend the last few minutes here solving out these integrals. But yeah, this is how you tackle a similar Fourier series problem if you are given one where you have the signal. It's just you're trying to figure out A, what the signal actually is, because you're just given a graph, and 2, once you have the behavior, how you actually compute the Fourier series. Because remember our synthesis equation, that's what they call it sometimes. I remember x of t is the sum of Cn e to the j and omega not t. From n is equal to negative infinity to infinity. Yeah, so let's go ahead and do these. 1 over 6. So 3 over pi. So the integral from -1 to 0 of t times 2. Wait, hold on. That's integration by parts. -1 to 0 t e j pi over 3 t n dt. 1/2 plus so 1 over 3 over pi times n negative of e to the 0. So 1 minus e to the j pi over 3 n. Yeah. And then this is integration by parts. I'm just doing that one integral. But this is 1/2, so I'm just going to move out this over here. It's 12. So this is going to be dt. Okay. Yeah, so now that I've written all of this out, I'm just going to move it back. I need space. Like way up there though. Okay. That works. Okay. Let me just, the following property, the following identities kind of useful that I'm going to derive right here. J omega 0 t n dt. So this is integration by parts. So if we remember integrals of the form u dv is equal to uv, so t e to the negative j omega naught t n over omega naught n negative, okay, and then minus the integral of, so this would be plus e to the negative j omega naught 0 t n dt. And then this should give us t e negative j omega naught 0 t n plus the integral of e to the j omega naught 0 t n over negative omega naught n minus omega naught n. So this is 1 plus t over e to the omega naught tn over omega naught n. Okay, yeah, that's that. Yeah, okay. So let me just plug that formula in. So negative 1 plus t e to the j omega naught tn over omega naught n, but omega naught is 1/3. Yeah, omega naught is 1/3. Pi, this would be pi over 3. So from 0 to 1, so pi n over times 3 of e to the j pi 3 tn with respect to negative 1 and 0. So actually we're running kind of short on time, and this is taking a bit longer than I thought it was going to. Yeah, so let's see. Okay, so I'm just looking at the solution I have right now, and they came up with a smarter solution than just straight up applying the formula. Okay, so notice that. Okay, let me copy everything over real quick. Let me just copy this to a new slide, and then we can talk more about this. Okay, copy, add page, paste. Okay, so this one. So they say that, notice that x of t is equal to that triangle function, so that so this is 1/2 times the triangle function of t. Yeah, so remember the triangle function is just, what I mean is from -1 to 1, and then it has peak value of 1. Yeah, so that's that, and then it's shifted over. Apply 1/2 triangle t minus 3, just because this one is centered at 0. Yeah, and then, yeah, they just kept convolving it with a delta function. So infinite sum of deltas, t minus n times 3. Yeah, 6 at period. N is equal to -infinity to infinity. Yeah. So yeah, that's our periodic function right here. Convolving it with a sum of delta functions that usually just brings an aperiodic signal into the periodic realm, I guess. So we can. This is the periodic extension of the signal here, and they say that yeah, just taking the Fourier transform of this one is much simpler, and I can see how. So because if we remember remember that the Fourier transform of a rectangle function, rectangle of t, convolved with a another rectangle, is equal to the triangle function. Okay, so great. So, but this actually has the effect of saying that the Fourier transform of both of these is well known. So the Fourier transform of these two rectangle functions, the rectangle squared, say, is equal to Fourier transform of the triangle. And since we know the Fourier transform of the triangle, then since the Fourier transform of the triangle function is the one that we're looking for here, that knowing this identity would be pretty useful. So this is actually just the Fourier transform of sinc t convolved with another sinc t. No, wait. Yeah. Also, remember that. Shoot, I wrote something. Let's see. So these are two rectangle functions that are convolved together, right? So rect convolved with a rectangle. Rectangle function times a rectangle. Yeah, convolved with a rectangle. And the Fourier transform of a convolution is the the Fourier transform of a convolution is multiplication in the frequency domain. So we get a sinc t times a sinc t is equal to the Fourier transform of a triangle. You might actually say this is sinc squared of t. Yeah, so that's that. So the way that you would do this is just take the Fourier transform here. Remember that the Fourier transform of this one is is also just a sum of deltas, t minus n times 1/6. Wait, this is omega. Yeah, so we just take the Fourier transform there. Okay, And then remember that convolution in the frequency domain is convolution in the time domain, multiplication frequency domain. So we multiply this times the Fourier transform of these two shifted triangles, and that gives us our result. So yeah, I'll let you. I guess this is an exercise to the reader because this is we're at 9 o'clock now. So I'd like to thank everyone who came, and yeah, if y'all have any questions, I probably have time before your exam tomorrow, or anyone else who's watching this, just in case you're in another section. I'm on the Discord server, just listed as a tutor. I'm Jerry. Yeah, so yeah, direct any questions to me. This should be recorded on the IEEE YouTube page, and if you need any other help, you can look at some of the other reviews that I've done on there. I've been doing this for a little while now, and I've done it for pretty much all the sections of signals, so you'll find more examples because I try really hard to not use the same ones each exam review. And yeah, yeah, thanks for coming, and yeah, see you